Hello there, and welcome to this live session of the Chemistry Clinic brought to you by Boost Revision. I'm Dr. Owusu. In today's session, we're going to be looking at AS practical chemistry, and we're going to be looking at synthetic organic chemistry to be more specific. We will be looking at how to synthesize an organic liquid, which is one of the practical activities that you're required to do in your first year of the A-level course. And I'm sure if you're new to the A-level course, you're now familiar with the idea of the practical activity groups and sort of achieving practical competency over the course of the 2 years of your A-level study. And of course, you end up with a practical endorsement, and also just so that the exam boards are satisfied that you have competence in practical chemistry, you will be examined on all the experiments that you have done over the course of the practical endorsement component of your A-level study. So questions in your 3 A-level papers will test your knowledge and understanding of the different experiments that you've been carrying out. So today's session will place quite a lot of emphasis on you understanding sort of practical technique, as well as the safety aspects that come with doing practical work in the lab. And so, as usual, I will be looking at some practice exam questions on the very specific reactions that you're required to do in terms of synthesizing an organic liquid. As usual, I will be connecting my tablet to your screens and sharing what I do on my tablet. I will also encourage you to use the chat box to ask any questions at all. I'm more than happy to pause at various points during the session to answer your questions. Okay, so without further ado, I will connect my tablet and then we'll be all set to go. And we're looking at practical chemistry and the synthesis of an organic liquid. Now, there are a number of reactions that you could do on the AS course that will fall under this heading. And the first one of which is the synthesis of a haloalkane. So you could potentially be carrying out a practical to make the haloalkane shown, which is of course 2-chloro 2-methyl propane, and you would be synthesizing this from the reaction between 2-methyl propan-2-ol and concentrated hydrochloric acid. And so that reaction would lead to the formation of our haloalkane. And of course, if we wanted to delve deeper into the reaction and mechanism, for instance, we would be thinking about nucleophilic substitution, where your chloride ion is your nucleophile and water is eliminated. Okay, so how is this reaction carried out? Well, we can break down the reaction into sort of constituent parts to make our understanding of the different steps in the procedure a bit more secure. So we can think of this reaction or any other organic reaction or synthesis in terms of the preparation stage, so actually bringing together reactants and reagents and solvent and catalyst, if there is a catalyst involved, bringing all of these components together in a reaction flask, carrying out the reaction, whether that's simply at room temperature or heating it gently or refluxing it. All of these techniques fall under the preparation of our product. Now, once a product has been made, of course, that product will be more often than not in a mixture with excess reactant, will be in a mixture with your catalyst, your solvent, certainly. And so we would need to go through a separation process. Okay, so you would need to find a way of separating your product from everything else it is in a mixture with at the end of the reaction. And then once you've separated your product, you would need to find an appropriate means of purifying it. Okay, so these are the 3 key stages that we'll be looking at. So in this reaction, we've got to make some 2-chloro 2-methyl propane, which I will highlight here, and I'll highlight that in blue. Okay, so we can also name it as a bit of practice. Let's call that 2-chloro 2-methyl propane. Okay, so that's our target, and we want to synthesize it first of all. Now, for the synthesis stage, and again, if we use blue as our highlighter for the preparation stage, let's look at what's required. So I'm going to make this a bit bigger so you can all read it with me. So you're going to be measuring out 8 centimeters cubed of 2-methyl propane 2-ol in a measuring cylinder and measure its mass. Okay, so that's your reactant. And so we've got measuring that volume of our starting reactant into a measuring cylinder. And then you're going to pour the 2-methyl propane 2-ol into a separating funnel. Okay, so your reactant in a separating funnel, and importantly, you're going to reweigh the measuring cylinder. Okay, so these are the first 2 steps in the synthesis. Now, if we consider why you would want to weigh the mass of your reactant this way, what we are doing here is weighing it by subtraction. So okay, so what we're doing is measuring a volume of our reactant into a measuring cylinder, transferring that volume of our reactant into our separating funnel, which is where our reaction is going to take place in this instance, and then reweighing the now empty measuring cylinder. And so if we subtract the mass of this empty measuring cylinder from the mass of the cylinder with the liquid, we will then know exactly how much has been transferred into our separating funnel. In other words, we get a more accurate mass of our reactant. Okay, so weighing by subtraction is very important whenever you're carrying out an organic reaction, so that you know the exact mass of reactant. Okay, so we know the exact mass of reactant used. So let's look at the next stage of our synthesis then. If we go back to our method, so in a fume cupboard, add 20 centimeters cubed of our concentrated hydrochloric acid. So we need to, again, pay attention to, or pay heed to, where this reaction is being carried out in a fume cupboard and why it's being carried out in a fume cupboard. Okay, so we're using concentrated hydrochloric acid, incredibly corrosive. You will probably have fumes of hydrogen chloride gas being produced, very toxic, very corrosive. You don't want to inhale it, and so you need to carry this out in the fume cupboard. So that's a safety aspect that you could be examined on as well. So let's make a note of that as well. So where are we doing this reaction? We are carrying out the reaction in a fume cupboard for safety reasons, highly corrosive hydrogen chloride or hydrochloric acid, concentrated hydrochloric acid. Okay, so we're going to add our concentrated hydrochloric acid to our reactant, our 2-methyl propane 2-ol, and we're going to do this in portions. We don't want to add it all in one go, because this reaction is quite exothermic, so you want to control the rate of addition so that you don't get your reaction mixture essentially boiling over. Okay, so in portions. So if we highlight that as well. And then after each portion, you're going to stop on the flask and invert it several times. Okay, so you're going to stop on the flask and invert it so that your 2 reactants are uniformly mixed together, and then add your next portion of your hydrochloric acid. Okay, now having done that, you're going to allow the separating funnel to stand in the fume cupboard. Allow the separating funnel to stand in the fume cupboard for about 20 minutes, gently shaking it at intervals. Okay, so we're adding our hydrochloric acid in small portions, and we're also mixing it, making sure that we've got a uniform mixture so that our reactants are in contact with each other and allows a much faster reaction. Okay, so we've carried out, after 20 minutes, we've carried out the reaction. The next part is separating our product from our excess acid from any unreacted alcohol. And how do we go about doing this? Okay, so it says after 20 minutes, allow the layers to separate in the funnel. Open the tap and remove the lower aqueous layer. Okay, so separation involves separating the aqueous layer from the organic layer. So the organic layer contains the product, and typically the organic layer will be less dense than the aqueous layer, and so will be the top layer. Although this isn't always the case, and you need to make sure that any questions you get, you look for any reference to the densities of the product versus the aqueous layer or versus your starting liquid. Okay, so we're going to be separating our two layers using the tap in our separating funnel. Okay, and once you've done that, you will then go on to purify the organic layer. Now, the organic layer will contain some acid, and so that will have to be neutralized. So let's look at our procedure again to see how this is done. Okay, so we have moved on to again, let's use a different highlighter this time round. So we have moved on to the separation phase now, and we're looking at we're going to be moving on to the purification stage in a second. But in the separation stage, you're going to be opening the tap and removing the aqueous layer, which you can dispose of, although I would advise that you always dispose of your aqueous layer right at the end of your experiment when you're sure that you've got all of the product that you want, that has been made. Okay, so that's going to be done, and then we're going to be adding some sodium hydrogen carbonate, which will get rid of any excess acid that remains. So this neutralizes remaining acid. And then you're going to be shaking the funnel after each addition. Now, of course, if you're adding sodium hydrogen carbonate, then you're going to be forming carbon dioxide as a product, and this is an indicator of the presence of an acid. And so you're going to be doing this until there's no more carbon dioxide being formed, and then you know that you've got rid of all of your excess acid. Okay, and once you've done that, you're going to be again separating the sodium hydrogen carbonate layer, which is aqueous, from your organic product, which will be, of course, in a different layer. It has a different density. Okay, so allow the layers to separate in the funnel. So again, using the tap on the separating funnel, and you're going to be removing and discarding the aqueous layer. And then you're going to run off the organic layer into a clean conical flask, and you're then going to dry it. So drying is a means of removing any small amounts of water left over, having treated it with your aqueous sodium hydrogen carbonate. Okay, so we're going to add some anhydrous sodium sulfate, which will absorb any leftover water. Okay, so if we go back to our separation, we have removed excess acid. Using sodium hydrogen carbonate. And if I make some room for, and then we've also removed water using anhydrous. We've used anhydrous sodium sulfate in this instance. There are a number of anhydrous drying agents you could use as well, magnesium sulfate being another example. Okay, so that's our separation stage. And now what we're left with is our crude product, which we can purify in this instance by distilling. Okay, so we're going to be purifying our product by distilling it. And if we choose a different colored highlighter this time round for the purification stage, and then we can highlight the different steps involved in purifying it. Okay, so we're going to decant the liquid into a weighed clean flask, distillation flask, and we're going to be distilling the liquid. Okay, and we will collect any liquid that distills in that given range. That given range is the boiling range for our haloalkane. Okay, so our 2-chloro 2-methyl propane is going to boil between 47 degrees Celsius and 53 degrees Celsius, and so you will need to collect your any liquid that boils or distills and condenses over that range. Okay, right. So once you've collected your distillate or your product, you can measure the mass of it and go on to calculate a yield if that's what you're after. Okay, so in terms of the purification, what we need to do is distill our crude product. Okay, so that's quite a detailed look at the different steps involved. Now, I'm going to take aspects of each of these 3 main steps and sort of drill deeper to ensure that we've got a full understanding of why each of these steps is taken, and also some of the pieces of apparatus involved. Okay, so looking at the separation process and specifically looking at the separating funnel. The separating funnel, you can see a diagram of it here. I'm going to very quickly highlight it. There's your separating funnel, and it's a very simple piece of apparatus. It's essentially a piece of glassware with a tap attached to it, which allows you to drain liquids out of the bottom of your separating funnel. Now, in any separating funnel, you're bound to have 2 different liquids of different densities, and so if I show 2 different liquids, one in blue and perhaps the other in red. These 2 different liquids will have different densities, hence the 2 layers. And the lower density will always float above the higher density liquid. Okay, so how do we separate the 2 layers? We simply need to turn on the tap. So if we annotate that, so the use tap to separate the 2 layers, and as soon as the blue layer has reached the tap, you can turn off the tap, and that leaves your red layer in your separating funnel. Okay, so that's how it works on that very simple premise that you have 2 liquids of different densities. In this specific reaction, we shook our organic layer with sodium hydrogen carbonate. So sodium hydrogen carbonate is aqueous, so we can imagine that that is the blue layer in our diagram. And so that sodium hydrogen carbonate is, of course, there to react with any leftover hydrochloric acid. Okay, so you can imagine your NaCl. So this removes HCl. We need to, in the reaction with HCl, CO2 is produced, and that causes pressure to build up in your separating funnel. And so you need to make sure that while pointing the funnel upwards and away from people, that you open the tap to relieve the pressure. Okay, so CO2 is produced, which leads to a pressure buildup. And so the way to relieve that pressure buildup is to turn on the tap to relieve it. Okay, so that's one aspect of our separation to get our product away from so that any leftover acid. We also need to, having done that, get rid of any small amounts of water contaminating our sample. And the way to do that is the addition of anhydrous sodium sulfate. And so absorbs small amounts of water in our product. Okay, so that's the separation part of our synthesis of our haloalkane. And so the other aspect, the final aspect of our synthesis and isolation of a pure sample of organic liquid of our haloalkane involves the distillation of our crude product. Okay, so in distilling our crude product, we're going to pick a suitable flask, a round bottom flask, or a pear-shaped flask, and to that we're going to connect a condenser attached to a still head. Okay, so if I can label the still head for you, because it's not shown here. So this part of our apparatus is the still head. Okay, and to that still head, you're going to have a thermometer. And if you note very carefully that the thermometer is lined up with the junction of our side arm of the still head connected to the condenser. Okay, so thermometer is level with the condenser, the bulb of our thermometer, I should say. Okay, so the bulb of your thermometer is level with the side arm. That means that it is recording the temperature of the vapor that is about to be condensed. That means if you're collecting a liquid in a boiling range, in this case of 47 to 53 degrees Celsius, you can be certain that the liquid being collected has been condensed in that range. So you need to make sure that the boiling up to the bulb of your thermometer is aligned to that side arm. Okay, so that again sort of ensures that you've got, or you can be a bit more certain about the purity of the liquid coming out. Okay, so we're going to heat our reaction mixture, in this case our crude product, in our round bottom flask. It's going to evaporate, it's going to boil, and it will then be condensed by our Liebig condenser. And another thing to pay attention to is how you connect your water to the Liebig condenser. You should always make sure that the water goes in at the lower end of our condenser and that the water goes out at the upper end. Okay, so water in at the bottom and out at the top. Now this ensures that your Liebig condenser has no air pockets. So if you connect it the other way, you will get some backflow, and then that will leave pockets of air in your condenser, which means that you don't condense as efficiently. Okay, so water in at the bottom gets rid of all the air. So at the bottom gets rid of all air. And you get better condensing, more efficient condensing. Okay, so water in at the bottom and out at the top. And finally, a very important safety point to make is that you can see there is an opening where your receiver is. Okay, so that we don't get a buildup of pressure and we're not heating a closed system which is liable to explode. Okay, so so the opening from receiver ensures the pressure does not build up. and you're not heating a closed system, which can then sort of explode catastrophically. Okay, so that's the synthesis of a haloalkane. Let's look at another example of an organic reaction that you could be asked to carry out to meet the requirements of the practical activity group 5, so synthesis of an organic liquid. And the next reaction we can look at is the synthesis of cyclohexene from cyclohexanol. Okay, so in this reaction, we've got an elimination of water to form an alkene, and this is catalyzed by phosphoric acid. And again, we can think of this reaction in 3 stages. So we can think of the preparation, so bringing together our reactant and our catalyst, and we can also then think about how to separate our product from everything else we've got in our reaction, and then we can also think about purifying our product appropriately. Okay, so we're going to look at each of these 3 aspects, and you'll find that there are a lot of techniques that are common between this particular reaction and the one we've just seen before on the synthesis of the haloalkane. So let's look at the start of this reaction then. So we're going to be looking at our cyclohexanol, and again we're being asked to pour it into a weighed 50 centimeter cube pear-shaped flask. So first step is to weigh our starting reactant, and if you note, we're being asked to reweigh the flask and record the mass of our cyclohexanol. So again, we're weighing by subtraction. It's a very important point to make, and one something you ought to note down. Weigh by subtraction, weigh reactant. Okay, so just as we saw in the last experiment. Okay, and then using a plastic graduated pipette, carefully and with frequent shaking, add to the flask approximately 8 centimeters cubed of concentrated phosphoric acid. So we're using a plastic graduated pipette, and we're going to be adding approximately 8 centimeters cubed. Now, approximately is important to note here, because that is suggesting that your phosphoric acid is in excess. We don't need to know the exact amount or exact number of moles of phosphoric acid being used here, okay? Or it could be that it is, because we're using a catalytic amount, it doesn't matter that it's less than equimolar in terms of the number of moles of our alcohol being used. So always pay attention to sort of quantities that are given sort of in rough. So approximately, that suggests that it isn't important to know the exact amount of phosphoric acid you've got, either because it is in very large excess, or it is a catalyst, and so you only need a small amount of it because it sort of cycles rapidly over the course of the reaction. Okay, so we've got our approximate 8 centimeters cubed of phosphoric acid into our reaction flask, and we're going to be adding a few anti-bumping granules to the flask. So adding anti-bumping granules to the flask, and then assembling the distillation apparatus. Okay, so our anti-bumping granules, something we need to consider. Anti-bumping granules. These are going to reduce the size of bubbles formed as your reaction mixture boils. It stops your reaction mixture boiling over and sort of collecting sort of a mixture of impurities in your receiving flask. So reduces okay, so anti-bumping granules are essential in this reaction, this distillation. And having done so, we're going to be distilling off the contents of the flask by heating the flask gently, and any liquid below coming off condensing below 100 degrees Celsius, we can collect. Why do we know that? Why can we do that? Water, of course, boils at 100 degrees Celsius. Our reactant cyclohexanol boils at well over 100 degrees Celsius. It's close to about 160 degrees Celsius. And it's a similar case for our phosphoric acid. So our reactant, our catalyst, and water, which is a byproduct, all boil at 100 or higher, whereas our alkene boils at a much lower temperature, below 100 degrees C. Okay, so by limiting the volume we collect to any volume boiling below 100 degrees C, we're going to minimize the amount of impurities we have in our mixture. Okay. Okay, so collect. Okay, so below 100 degrees C to minimize the amount of impurities we get in our mixture. Okay, so let's look at the next part. So we're going to be pouring the distillate into a separating funnel, and there we're going to be adding some sodium chloride solution, and that should allow us to separate or remove any small amounts of inorganic phosphoric acid, for instance, and water, and also unreacted cyclohexanol. Okay, so we're going to be using a separating funnel. Okay, so having used a separating funnel and shaken our product with saturated brine, we can get rid of some of the acid and water present, and we can then use the tap to separate the organic layer from the aqueous layer. Okay. Okay, so once we've done that, we can then consider how we're going to go about purifying our product. Okay, so let's look at, first of all, highlighting the separation portion of this process. So we're going to be using a separating funnel and adding some sodium chloride and shake and allow the two mixtures to separate, the two layers to separate. Then you're going to run off the lower layer, and we're going to have our upper layer, which is our crude product. And then we're going to be adding a few lumps of anhydrous calcium chloride, so again, a drying agent, or sodium sulfate, which we saw previously, or even magnesium sulfate, to remove water. Okay, and then add drying agent. Anhydrous sodium sulfate, Na2SO4. And then finally, in the third part, you're going to be carrying out a purification. So having separated the organic layer from the aqueous layer, you could then go on to distill it further to purify it. Okay, so in this instance, we're told to decant the liquid into a dry weighed sample flask and reweigh the container to calculate the mass of our cyclohexene. You can go on to purify this cyclohexene further by distilling it. Okay, so that's so the second possible reaction that you could carry out as far as synthesizing an organic liquid goes. There's a final one which involves the synthesis of an ester, and in this particular synthesis, there's one area of the synthesis that I'd like us to concentrate on, which is in the preparation side of things, where you're going to be refluxing your reaction mixture. And I've picked out the diagram for a reflux setup to contrast it with the setup for when you're distilling. So in this diagram shown on the right-hand side, we've got our condenser connected vertically to our flask. So that is our Liebig condenser. And what you will notice, if I perhaps undo that highlighter for a second, is that the top of our condenser is open. Okay, so open end of condenser. And that is very important because you don't want to stopper it. If you put a stopper there, or if you put a thermometer there, you're going to be heating what is a closed system. You're going to get pressure building up, and you're going to get your reaction setup exploding before long. Okay, so open end of condenser prevents pressure building up. Okay, and then as usual, you've got your water in at the bottom and out at the top to allow you to avoid any air pockets, which reduce the efficiency with which your condenser will condense the vapor rising up through it. Okay, and typically you don't want your vapor rising up by more than about halfway up your condenser. Okay, and your reaction mixture is going to be here in your round bottom flask. You're going to be heating your reaction mixture. The reaction mixture heated to the boil. Okay, so you're going to heat it to boiling, and there's no requirement, there's no need to have a thermometer present because we're not interested in the boiling point of the mixture. We just want it to boil. We want the vapors to rise into the condenser and be condensed back into our reaction flask. And so the reaction mixture is heated to boiling. The vapors condense back. Back into flask. And then boil again. Okay, so you're going to do this repeatedly until all of your reactant has reacted. Okay, and in doing so, if you're going to be heating for such a prolonged period, if you weren't condensing it, then you would run out of solvent because all of your solvent would evaporate away. Any product that you made that was volatile would also evaporate away. And certainly if your reactant is volatile, you would get quite a lot of it just evaporating away before reacting with whatever reagent you've got in there. And so it is important that you reflux. So you insert a condenser vertically into your flask and reflux your reaction mixture. Okay, so three different reactions, all making an organic liquid. What I want us to do next is to test how much we've understood about the different techniques we've seen. And I've got a couple of past exam questions that we can use to test our understanding. So let's get on with that. So the first one to look at is it's a 2018 paper 2 AS looking at the synthesis of a bromoalkane. So we're looking at the synthesis of 1-bromobutane, which is an organic liquid, and we're told it has a boiling point of 102 degrees C. And a student prepares our 1-bromobutane by reacting butanol, so 1 bromobutane by reacting butanol with sulfuric acid and sodium bromide. Okay, so our sodium bromide and sulfuric acid is going to furnish us with our bromide ions, which are going to be our nucleophile in this experiment. Our H plus ion is going to protonate the OH, and we're going to be eliminating or getting rid of, or rather replacing water, eliminating water from our alcohol. So the student boils the mixture for an hour. Okay, so the student is going to be boiling this mixture for an hour. That is an important clue there. If you're going to be boiling a mixture of liquids for an hour, then you're going to need to reflux. Otherwise, you're going to be losing solvent, you're going to be losing reactant, you're going to be losing product. Okay, so that yellow clue there is very important. That suggests you're going to be refluxing. Okay, now you've got your balance equation given to you. We're also given information about densities. The student obtains a reaction mixture containing an organic layer which has, we highlight this, the organic layer has a density of 1.27 and the aqueous layer has a density of 1. That's grams per centimeter cubed. Now that is telling you that the organic layer in this instance, organic layer in your separating funnel, is going to be bottom layer. Is going to be the bottom layer. Okay, so these are all important things that the examiner wants you to notice and to actually say what their significance is in your answer. So let's look at the first part of the question. We're asked to draw a label diagram to show how you would safely set up the apparatus for the preparation. Outline a method to obtain a pure sample of 1 bromobutane from the reaction mixture. So we want to think about the preparation stage, we want to think about separation and purification. So let's look at the preparation stage. So we're going to be refluxing. So we've just looked at a diagram of the reflux. We're going to be heating using an electric mantle, a heating mantle, so that you don't have any naked flames. You don't want to ignite any flammable liquids present. So your butanol is likely to be flammable. So here's your reaction mixture in a round bottom flask, and then you've got your condenser. Okay, so you're going to be heating that, and you're going to heat that for, we're told, for an hour. Okay, so water in and water out. Okay, so that's what you're going to be doing as far as preparing or making your 1-bromo-butane. Having done that, you're going to then use a separating funnel. And in this instance, the organic layer is the bottom layer. Okay, and then what are we going to do to purify that bottom layer? Well, the first thing we can do is make sure there isn't any excess acid remaining. We could wash it with sodium hydrogen carbonate, for instance. To remove excess acid. Separate again. And then you're going to, having done that, you're going to use a drying agent to add anhydrous, you can use sodium sulfate. So you're going to add anhydrous sodium sulfate to remove water. And then having done that, you're going to filter to remove anhydrous Na2SO4. And then your liquid, your product can be redistilled to distill liquid and collect distillate at, we're told, boils at 102 degrees C. So okay, so that's how you would go about answering this question. So if we go back to the requirements, it says draw a label diagram to show how you would safely set up the apparatus for the preparation. So we would need to show that we knew how to set up for a reflux, which we've done. And we're going to outline a method to obtain a sample of a pure sample of 1-bromobutane from the reaction mixture. So we're going to use a separating funnel, which is key here. We use a separating funnel, the organic layer being the bottom layer because it's more dense. And we're going to wash it with some sodium hydrogen carbonate to get rid of excess acid. Separate using a separating funnel again. Dry it with anhydrous sodium sulfate. Remove your anhydrous sodium sulfate by filtration, or you just simply pour your liquid carefully and then distill the liquid to distill it and collect the distillate at 102 degrees Celsius. Okay, so that is quite a nice question testing your recall of the techniques involved in synthesizing an organic liquid. Let's have a look at another question that tests in a bit more detail our understanding of different steps in synthesis of cyclohexane. Okay, so in this question, and this is not an OCR question, but it could just as easily be asked. We're looking at cyclohexane, which boils at 83 degrees C, and we're told it can be prepared by the dehydration of cyclohexanol using conc phosphoric acid. Okay, so we've just seen an example a few minutes ago. A student prepares cyclohexane by placing 10 centimeters cubed of the cyclohexanol into a round bottom flask, given the density of it, and so you should be able to work out the mass used of your cyclohexane if you're asked to calculate the percentage yield, for instance. Okay, 3 centimeters cubed of conc phosphoric acid is added carefully, and you add a few antibonding granules and set up the apparatus shown to be distilling off product. And so the student heats the mixture and collects the liquid that distills at temperatures below 100 degrees C. The distillate is poured into a separating funnel and washed by shaking the sodium carbonate solution. So we're getting rid of any excess acid that's made its way into our distillate. You're going to periodically using the separating funnel, or you're going to invert the separating funnel and open the tap so that you relieve the pressure. The aqueous layer was discarded and the final organic product was dried using anhydrous calcium chloride, so it absorbs any small amounts of water left over. And once the product has been dried, we can filter to remove the drying agent. So if we look at the first question, then we're asked to calculate the percentage yield of cyclohexane. We need to skip that to look at a question that is relevant to our practical technique. It says describe, in 3.2, describe a test tube reaction on the product to show the cyclohexanol had been dehydrated. So how will you know that you've made the alkene cyclohexane? Okay, so your your test would be bromine water added to product will be decolorized. Okay, so that's how you would know that you've made your cyclohexane. As is, in 3.3, we're asked to suggest why sodium carbonate solution was used to wash the distillate. So we're doing this to get rid of acid, to get rid of phosphoric acid. So phosphoric acid will react with your sodium carbonate, you'll see fizzing, and as long as there's fizzing, you know that there is acid remaining. Once the fizzing stopped, you can then separate the two layers, so you know you've got rid of all of the acid. Okay, in 3.4, we're asked to say why it is important to open the tap of the separating funnel periodically. This relieves the pressure. Okay, so you want to relieve the pressure built up because as you're shaking it, you've got your sort of volatile sort of product sort of evaporating away and sort of producing vapor, which you would need to get rid of. You've also, sorry, in this instance, you're making carbon dioxide from the reaction between your acid and your sodium carbonate that you've just added. And so you will need to get rid of the CO2 that's being formed. Okay, so these pressure build up from CO2 forming. Okay, so there's a final question on practical technique here. So it says, give a property of anhydrous calcium chloride other than its ability to absorb water that makes it suitable as a drying agent in this preparation. It is insoluble. Okay, so it will not contaminate your product by dissolving in it. Okay, so it is insoluble in product. And water. Okay, so that gets that gets rid of the water, any small amounts of water. It absorbs that water and sort of clumps up. Okay, so hopefully you found this session on the synthesis of an organic liquid useful, and hopefully aspects of the practical and various bits of practical technique that you weren't so comfortable on, that you do have a better understanding now. As usual, if you've got any questions, do write to us at boostrevision.com and we will be more than happy to write back with an answer for you. It's been a pleasure for you to join me this Sunday. I look forward to seeing you again when we'll be looking at some more practical chemistry. Thank you very much for joining me and hope to see you soon.